began to develop OPOs in 1995. It was a very interesting scientific goal to use this idea, which has been shown in universities, for instruments.
APE was the first company bringing periodically poled crystals into the OPOs and thus making a high degree of automation possible.
APE has taken technology that existed, but implementing all the computing power that you have available today and really use that to make the complexity of these devices disappear.
We further were the first company building OPOs for CARS microscopy.
And that really enables people to do a lot of interesting spectroscopy work and research.
Main application nowadays is moving from the scientific chemistry or physics lab into biology, microscopy, and other applications.
It's really a very natural thing for APE to work with these customers, to have a very consistent and long-term, but also sometimes very intense dialogue about what's important for them, for their application, for the research that they're doing, and on the other hand, what's technologically possible, what can we do to help them.
My name is Stefan Winter and I'm from the PTB in Braunschweig. The PTB is the National Metrology Institute of Germany and is responsible for the calibration of objects, and we are performing the calibration of solar cells.
The collaboration with Dr. Winter began 2 years ago when he asked us for having a source which is imitating the full solar spectrum.
For the different type of solar cells, we need the spectrum from 280 to 2000 nanometers. For our working group, very important that we can calibrate UV detectors from 210 to 280 nanometers.
Which is much broader as a single laser can generate. But if you use nonlinear technologies behind the laser, which is doubling, tripling the spectrum, and using the OPO to expand to the infrared, you can expand the spectrum of the central laser to a very wide field, but it needs to be done in an automated way.
The automatic control is very important because our measurement time is about 24 hours to 72 hours and sometimes even longer.
So we had not only to supply him with the OPO and the doubling and tripling stages, but also with the automation of the full system, switching on and off the different wavelengths and also controlling the tuning mechanism.
The complete system, how we are using it, also the laser and the surrounding mechanics, is the only system in the world to measure solar cells starting at 210 nanometers and going to 4000 nanometer only with a small gap.
My name is Peter Friedl. I'm professor here at the Radboud University in Nijmegen. I'm directing the Microscopic Imaging Center. I'm fascinated by identifying the mechanisms how a disease changes the tissue and also the body, and how this knowledge can be used for developing new therapies. We are interested in how tumor cells grow in the body, escape immune defense, and then how we can redirect immune cells to detect the tumor cells and kill them.
Peter Friedl approached us a few years ago. For us it was a starting point to further develop the OPOs for application into the microscopy.
The first OPO we installed in 2005. I wanted to get a deep three-dimensional picture of the process in the tissue. With a conventional two-photon setup, we could go 100 to 200 micrometers into a living tumor. And I wanted to go as deeply as possible. So with the OPO, we already reach 0.5 millimeter, which is a big step forward. So we can visualize deep processes in tumors.
The application of our compact OPO in microscopy was driven and initiated by APE together with Professor Friedl.
The key advantages we have witnessed were that the power has increased, the stability of the lasers got better and better, And the user friendliness got better and better. The systems are more stable, they are more turnkey. And to implement it into the biomedical world, yes, it has to be simple.
It is a big step from academic setup showing the parameters once until one is able to manufacture instruments in a reliable way.
It was pioneering work. Since then, it has been recognized also by others, of course. That infrared excitation gives them a very important additional strength to their research. So many systems have been implemented after that and are being used for biomedical research.
My name is Eric Padma. I work here at the University of California in Irvine. I have a laboratory here in the back. You can see it right there. We employ laser setups that includes optical parametric oscillators, and we use these to excite molecules in our samples with optical microscopes. And these molecules form markers, mostly for tissues. So in the end, it becomes a biological imaging microscope. And we can see where molecules are in a tissue, and we can see them quickly. And so we optimize the techniques, make the pulses do what we want, and create images fast and crisp.
Professor Eric Padma was one of the very first scientists working on this system. In about 2004, Professor Sonic C from Harvard University approached us whether we could develop and produce a light source suitable for his needs. Professor Eric Padma at that time was one of the students at his lab.
Where we were really focusing on making this technique faster. And within 5 years or so, we really managed to do video rate scanning, so real-time imaging with the CARS technique.
OPOs fit very well into the CARS concept in the sense that they allow systems to be much simpler, to be much easier, because they automatically synchronize the pulses. They allow for systems to be a turnkey operation.
So the synchronously pumped OPO is an absolutely ideal solution for CARS and coherent Raman scattering in general. Stability was much better than we had seen from other light sources. We've had a fairly close relationship with the APE, bouncing back and forth ideas about how to improve, how to make things better, and that has continued till this day.
Constant improvement, indeed. And next to this constant improvement, there have been new concepts for detection. So there has been this concept with wavelength switch detection or rapid scanning detection. But in general, it's just been a lot of careful engineering and making new things possible.
What's unique about the relationship that we have had over 10 years, the constant back and forward between improving the technology, enabling research, going back and saying, okay, so if you can do this, what could you do with this?
The goal of the systems that we work with is to implement these instruments in a clinical environment and to basically take images of patients without the need of taking pieces of tissue out, but really looking at the tissue with the photons directly and come to a diagnosis.
So that you can, during an operation, image label-free directly and image, for example, tumor boundaries or differences between different types of tissues, where you want to excise, where you do not want to excise.
It's already been implemented in eye research in the clinics. This is only a beginning.
The food industry, for instance, has been very, very interested. They want to look at fats, proteins, and water. These are essential components in food.
In the pharmaceutical industry, they're very much interested in looking at chemical compositions, at structures in chemicals, in drugs. And it is pretty clear that devices built based on OPOs have the capability to advance the knowledge in that area.
Nanoscience, another example. Many nanoscopic materials are optically active, and the CARS microscope actually can look at these materials very nicely.
There's a lot of dreams, and these dreams are driving this technology.
It is something that I feel is going to happen. There's no doubt that these developments will continue and mature and get us there where we want to be.